I'm Shoyakan from University of the Ryukyu. I will talk about optimal resource allocation for machine learning tasks in distributed computing environments. This is outline of presentation. First, introduction. I describe background and proposal and so on. Second, I mention Petri Net Model for resource allocation. Third, experiment in simulation and real distributed environment. Finally, conclusion. First, I explain introduction. As IoT and machine learning is being applied to many aspects of our daily lives, the demand for efficient computational resources is increasing. Major cloud services and many other cloud environments support enormous computation demands, but it is not always possible to allocate resources efficiently. This problem is called resource allocation problem. The problem is quite important for IoT and AI era. The resource allocation problem is difficult to solve within a reasonable computation time due to its NP hardness. However, recent advances in mathematical programming algorithms have shown that we can solve even the practical size of such problems within a realistic computation time if we formulate them in integer linear programming. Our previous study developed an algorithm to generate integer linear programming problems for scheduling and resource allocation problems based on the Petri Net model. The method makes it possible to use the mathematical programming solver easily. Machine learning processes are good practical example, since their tasks flows are relatively typical. Series of sequential tasks of preprocessing, learning, and prediction. We propose scheduling methods for processing many machine learning tasks. We scheduling method our scheduling method can apply multiple sequential processes with numerous computational resources efficiently. Next, I explain Petri Net model for resource allocation. The resource allocation problem is a type of scheduling problem. It is one of the combinatorial optimization problems that minimize the total amount of resources used while generating the overall schedule by assigning resources to tasks. Usually, the length of the overall schedule is given as a constraint or to be minimized. The following are the condition for resource allocation problems. First, each task requires the requested amount of resources. Second, there may be more than one resource of each type, and the same resource can handle different capabilities. Third, each resource is always available. Fourth, the scheduler does not allocate resources to another task until the processing of the task complete. Fifth, the cost and capacity of the resource are given in advance. The resource allocation problem can be modeled by the Petri net. A rectangle in the net represents a task. This places a resource pool and they include resources. So this task requires the green resources for processing. Now I will explain the experiment. This section evaluates the performance of three resource assignment policies. Random assignment, it means first come, first served here. Greedy assignment, longer task first. And mathematical programming with simulation and real environment. First of all, I explain a simulation experiment. The simulator has three main functions: generating data, deciding allocation according to the scheduling policy, and visualizing the task schedule from the allocation result. I explain function about generating data. Each task data consists of three information: task ID, predicted processing time, and actual processing time. The predicted processing time is generated randomly using a uniform distribution in an arbitrary preset range. The actual processing time is also generated based on the normal distribution by Box-Muller method. Mean value is the predicted processing time and standard deviation is varied as a parameter. We characterize computing node by two information, node ID and processing performance. Processing performance is a positive number, where its value 1 means the node can execute the task in the processing time given as the actual processing time. Processing performance 0.5 means requires twice the processing time. Processing performance is 2 means requires a half the processing time. I explain function about deciding allocation according to the scheduling policy. Once the resource set and the task sets are given, the scheduler assigns a resource node to each task based on the scheduling policy. In this experiment, we employ the three scheduling policies, RA, greedy, and MIP. We automatically generated the integer linear programming problems for the Petri Net model. In this experiment, we generated the predict time for 30 tasks with uniform distribution of range 1 to 1200. Varied standard deviation sigma from 0 to 500 for generating actual processing time based on normal distribution. Here, the generating process predict time is used as mean values. Our scheduler assigned a computing resource to each task based on the three scheduling policy, array, greedy, and MIP. We use the same processing performance of the same node for all measurements through the experiment as shown in lower table. The quality of schedule based on greedy and MIP strongly depends on the quality of the prediction. We assume that the difference between the predict processing time and the actual one can be represented as a random variable of a normal distribution with the mean 0 and the standard deviation. Experimental results in simulation. Left figure shows the average sum of the make span by varying the standard deviation. The x-axis shows the standard deviation. Larger value of the standard deviation means worse prediction quality. The y-axis represents the make span. Right figures show the load imbalance among computing resources, represents the difference between the earliest nodes and the latest completion one. The x-axis is the standard deviation of the difference between the predicted and the actual processing time. The y-axis is the difference between the earliest and the latest nodes. Left figure shows that MIP has the shortest make span where there is no difference between the predicted and measured values. However, from a standard deviation of more than 200, the MIP-based scheduling becomes worse than the others. We confirm that the MIP-based scheduling is not effective when the quality of prediction is low. From right figure, array and greedy do not change much for the schedule. Array and greedy do not change much for the prediction quality. Since both of array and greedy are dynamic scheduling, the idle time in node flexibly is reduced. At the same time, MIP scheduler is a static assignment. Therefore, the scheduling quality is affected by the prediction quality. Next, I explain experiment in real distributed environment. We also performed experiment in a real distributed environment. We implemented a distribution environment shown in the figure. We use Launcher, open source software, to manage Kubernetes cluster, both cloud and on-premise, from a single dashboard. Therefore, we can build a highly scalable parallel and distributed environment. The cluster consists of 3 nodes. This distributed environment performs tasks in 3 main steps. In the first step, each pod on each node accesses the queue keyed by the node name, where the pod itself exists to Redis on the same cluster. In the second step, we get a CSV file training data for machine learning, corresponding to the task number obtained in the first step via NFS. In the third step, each pod performs training data. Each pod performs training in machine learning for the obtained training data in the second step. After the processing, each pod stores the results in MySQL on same cluster. Each pod runs these 3 steps as many times as we set during deployment. It generated integer linear programming to assign node. I explain generating process. Step 1. Export the Petri Net model into Excel file format and convert its integer linear programming programs in LP file format using our original integer programming tool, PetriNet to MIP. PetriNet to MIP is our previous study. It is Petri Net model converted to integer linear programming program. Step 2. Solve the mathematical programming in the LP file using a solver. Step 3. Extract necessary information for resource allocation from the output SOL file and convert it to JSON format. Step 4. Generate a YML file to decide which node to allocate a pod to based on the JSON file. In our real distributed environment, we employed a machine learning task in bioinformatics, estimating the dihedral angles of proteins. We collected short amino acid sequence with calculated dihedral angles for training data. As algorithms for the dihedral angles estimation, we use Rust regression and decision tree regression. We predicted learning time for this machine learning task with linear regression. Feature vector is composed of the size of training data. We vary the set size from 1000 to 10,000 with interval 1000 and measured processing time. We measured many times the computation time for each scheduling policy, array, greedy, and MIP in the Rust regression and decision tree regression for 30 tasks. This table shows the make span needed for training by the Rust regression and decision tree regression. The result for the Rust regression shows that array is worst, followed by MIP and greedy. For the decision tree regression, the MIP is the worst, followed by greedy and array. When we derive the make span from the predicted time, the MIP generates the best schedule. I mean, theoretically, the MIP is the fastest. However, it is not true in the actual cases since the prediction accuracy is poor. Therefore, the fact leads to the worst quality of the MIP-based scheduling. For the last regression, we found that array is the slowest. Next slide shows a Gantt chart for array. This figure is Gantt chart for array. Each color corresponds a computing node. There are 3 computing nodes, CentOS, events, and analog. The colored rectangles are the time for processing. Blank space, the idle time. Looking at the figure, we can see that the task with a relatively large processing time allocated at the end of the event node. So the overall execution time is longer, and array is worse than the others. We observed the prediction quality per computing node by using coefficient of determination defined by this equation. Value 1 means the best quality, smaller value does worse. This table shows the coefficient each node. Total means for all computing system. You can see the prediction quality depends on computing node. For example, CentOS is quite small compared to the others. In such situation, the scheduler can assign task and reliability prediction time to resources. The fact also makes us consider the typical computer specification and computing resource situation when we collect training data. Finally, conclusion. This paper presented some evaluation results of our resource allocation scheme for machine learning tasks. Situation experiments shows that MIP-based scheduling does not seem efficient when the processing time prediction is low quality, while the greedy algorithm performs very well. We currently improve the prediction algorithm of learning time, where the algorithm can treat several prediction model and computing resources. Thanks for listening.